All right, our second talk of the session is by Zander Kelley about quasi-polynomial bounds for some problems in extremal combinatorics.
So I'd like to talk to you about some problems in extremal combinatorics. So here's three of them. They're all roughly of the same high-level structure. In each case, we are just given some arbitrary dense set in some space. And what we're asking for is whether, just by virtue of this set is so large, there's some substructure whose presence in the set is just unavoidable. So we can find, for example, some non-trivial three-term arithmetic progression inside any dense subset of a cyclic group with n integers. Or, the second problem is the corners problem. We'd like to find like this sort of pattern inside some two-dimensional dense set. And then here is like some dual equivalent formulation of the triangle removal problem due to Ruja and Semeretti, which is just asking, if you have some like large enough hypergraph, can you find three sets whose union is very small, only size almost 6? And I wouldn't say, I think it's not immediately obvious, but these problems are actually increasing in difficulty. So with some engineering, you can show that some bounds for one implies a bounds for the other of them arranged left to right. So for example, a lower bound on this 3AP problem is also giving you a lower bound on these other two problems. So let me say just a bit about this first problem, this 3AP problem. This is one of our favorite problems in additive combinatorics. It's seen a bunch of work, and a bunch of new techniques have been developed to attack this problem. Here you can see the results of a bunch of work. So each of these results are proving a theorem of the same form, just to remind you, namely, like for any dense enough set in Zn, say, it's forced to contain some non-trivial three-term arithmetic progression. And then the only difference is like we're making some quantitative improvements. So we're proving this for density, which is smaller and smaller. And then you can see down here, I have a lower bound. This is a non-trivial construction due to Behrend of a very large set which does have no three-term arithmetic progressions. And it's like notably larger than you would get if you just tried to pick a random set and then pick delta so that you see 3APs. So some non-trivial geometric construction. And I'm going to call this like funny quantity that he gets for this density quasi-polynomial in the talk. And just recently, together with Raghu Mecca, we made some pretty big progress on this problem, and we got the first quasi-polynomial upper bound for this problem. And since then, it's been refined a bit, and we have some better constant in the quasi-polynomial. So here, I want to tell you about, so these are these three problems I started with on the left, like arranged in order of difficulty. And I'll tell you a bit about some recent works that relate to all three of these problems. So these two works, this one was by myself and Shahar Logat and also Raghu Mecca. And then this work up here is also work of Amir Wood and Nick Fisher. We proved some things. So the papers are the main result is some application in theoretical computer science. So I won't try to tell you about what that is, just because it would take a few minutes. But I'll tell you about like the main mathematical content and how they are strongly, how these results are strongly related to this corners problem and this triangle removal problem over here. And if you'd just like something to remember them by, somehow here we prove some sort of useful, sufficient condition for a quasi-polynomially dense graph to have many triangles. And up here we prove some kind of removal lemma. I'll try to sell you on that near the end of the talk. And then, I'll just mention in passing, there's this follow-up work by some other people, by Yuval Filmis, Ahmed Atami, Esti Kelman and Abe Hosseini, who generalized this. So under the same conditions that we get this triangle counting lemma, where we're saying you have many triangles for any sort of constant size pattern, not just triangles, that you're going to see a large number of that pattern inside this graph under the same condition. So, okay, so for all of these problems on the right, we have quasi-polynomial bounds. And actually, quasi-polynomial bounds are plausible for all the problems appearing here. So it'd be very interesting to see if you could get that kind of improvement for the corners problem or even for triangle removal.
What is quasi-polynomial? Two, what column?
Yes, so let's go back here.
Any of those near the bottom?
So just some 2 to the minus log to some constant.
It doesn't have to be a fraction. 2 to the minus log to a fractional power.
Yeah. Yes. Okay, so yeah, anyway, it's really interesting to ask if we can get this kind of result for both of these problems too. And we did something which is related to that I'll try to tell you about in the rest of the talk. Mainly, I want to present some perspective where all 4 of these questions can be cast as a question about some particular combinatorial object called a cylinder intersection. So let me start here. So a cylinder, a combinatorial cylinder, is it's a symbol kind of thing. It's just we're going to talk about functions or sets inside this product space, some arbitrary product space, just some sort of function whose indicator function only depends on 2 out of the 3 coordinates. And then occasionally I'll also talk about this, like a cube is just a subproduct set that will play a less substantial role. But here is the main character of the talk is a cylinder intersection. So we have 2 characterizations. One is just this representational characterization. It's just like a product of some cylinders, right? And then, interestingly, it also has this equivalent local characterization. So these sets S are exactly those sets such that this property holds that they don't have any empty stars. So if you ever find some point which is adjacent to 3 points which are in S, then that point must also be in C. And yeah, okay, so I should say, we're interested in studying these objects. You could say, well, we have this nice global characterization, this nice local characterization. What more could you ask for? It turns out that for applications in complexity theory and also in additive combinatorics, the main question that seems to be really interesting to understand is what are some sufficient conditions for some set to be not a cylinder intersection or robustly far from being a cylinder intersection. And here's one way of quantifying this. So if you had some sort of small set, maybe I had to define this first, but yeah, you can consider this notion of the cylinder intersection closure. So either by taking the intersection of all cylinders that contain the set, or equivalently by just adding all the centers of all these empty stars to A, you get some closure of A, and we're interested in understanding when you can have a small set A that has a very large closure. So, oh yeah, and let me just put in this one example about what kind of things can you model with this notion. For example, if you just have a graph, then the set of triangles in a graph, considered as a subset of tuples of this V cubed space, is a cylinder intersection. So this is capturing this very simple fact that you cannot, arrange such that your set of triangles is any particular set you want. For example, you cannot add exactly the right edges so that you can contain these 3 triangles on the outside without also including this triangle on the inside. So this notion is useful for summarizing that fact somehow algebraically or something. Yeah, so let me tell you about this equivalent reformulation of the corners problem. And it's about this set D. So this set of triples with x plus y plus z equals 0. And an equivalent question to the corners problem is the following, is that we need to show that for all dense subsets A, this closure of A becomes dense inside the ambient space. And of course, you'd like to prove this for density as large as possible. For the application, you want to set epsilon to be 1 over n. And yeah, let me point out some combinatorial property that at least makes this plausible. So for the set D, I want to say it has an interesting property. It's fairly generic, not really dependent on the specific group at all. That if you think about the projection of the uniform distribution over D to any like 2 coordinates, then you see everything, right? You get the uniform distribution on those 2 coordinates. So I'm going to just call that like that D is pairwise independent. So in particular, it's like all its marginals have full support. So the cylinder intersection closure of D is everything. Okay, so of course this property I told you about is ruined very easily by passing to a subset. So that's like the part of all the drama is to say, you know, even large subsets have some similar property here. And I'll tell you about what do we do in this work. Yeah, let me introduce this question, which you will surely have to agree is only easier. I want you to prove this, you know, say with quasi-polynomial bounds for any explicit set D of your choice. Okay, so I think this way of thinking about things is very productive, and it makes you really think about, okay, what property do I even want if I could have any property I like in order to prove this kind of thing. And I'll show you in this paper. So what do? We proved this property for this specific set D over here, which was engineered. You shouldn't pay too much attention to like the specific construction, or really we needed it to satisfy some combinatorial property, which roughly you could summarize as even after you condition on some large subcube, it's still like approximately pairwise independent inside that subcube. That's roughly what we needed. Anyway, this is the point of that work, and by doing this, yeah, I guess I should say just passing that this gave us some communication complexity lower bound, because the communication complexity of some, sorry, the 3-party communication complexity of a set is exactly characterized by the smallest numbers such that you can partition the set into that number of cylinder intersections. So anyway, that's what this result, that was the application that we used this result to prove, or to argue. We got some high communication complexity function. Anyway, let me move on to this last point, which is reframing of the standard triangle removal lemma. I want to like argue to you that, well, it's not hard to argue. I'm just going to point out that this is like completely just a cosmetic reframing of the standard triangle removal lemma, which says that if you have a graph with few triangles, you can remove a small number of edges in order to destroy all the triangles. So in terms of cylinder intersections, that's telling you that if you have a small cylinder intersection, like it has small measure, then it can be approximated in this one-sided sense by some simpler functions, just by some cylinders. Okay, so you can find some cylinders, and then also it's important that like these cylinders have reasonably small total mass. And yeah, there's some calculation you can do to show that for any pairwise independent set D, actually, this will solve this analogous problem we just talked about for the corner, and in particular gives you some answer to the corners problem for any group, for example. And then so very finally, I need to include or introduce like one last shape. I'll just define it by example here and how it relates to these other shapes. So these slice functions, they have indicator functions that look like this, right? So they generalize cubes and cylinders. It's a smaller class than cylinder intersections. And so what did we prove in this second paper? We proved this sort of removal lemma on the right, which you can compare to this triangle removal lemma on the left. So whereas the triangle removal, this lemma is saying that you can get some cover in by some cylinders, we get some cover by some slice functions. However, like the dependence, the parameters are very good though. That's the upshot, is that we get some like quasi-polynomial parameters on the right-hand side, and you could hope for the same thing on the left-hand side, but yeah, so far we don't, not sure how to do it. Thanks.
Are there any questions for Zander?
If there's no questions, maybe I'll ask one. Really nice talk. I know that in the work with, I guess, Shahar, Amir, and others, you guys gave a faster algorithm for like a combinatorial matrix multiplication algorithm. Have you thought about whether that can be extended to like an online matrix multiplication algorithm?
I see.
With the same.
How different is that to that's kind of this question where you try to get some like pre-processing for matrix multiplication. Is that the same thing?
Yeah, that's the same.
That's what you're talking about? I have thought about that. I think it's maybe plausible that you could do it with a similar strategy. You need a different analysis, but I actually think, yeah, maybe without even changing much about the algorithm, you might be able to get something similar.
Then let's thank Zander again for the